is about estimating uncertainties, essentially. So doing inference with machine learning, which is something that is, let's say, very relevant for science. Machine learning, as you know, is used everywhere, but in many commercial applications. But doing inference and estimating uncertainty is something scientists do care about, and it's less common in other fields. And in the past years, there's been lots of progress in making a neural network or deep learning probabilistic, so that you can do formal Bayesian inference. And actually, this introduces lots of efficiency in terms of, how you do inference in science. So the lecture, let's say, is going to be a bit about Bayesian statistics and how it's connected to machine learning. So I'm assuming you are more or less familiar with Bayesian inference. I'll show you some reminders, but that's the starting point, and we're going to try to make the bridge between a neural network and standard Bayesian inference. And then this introduces what we call implicit likelihood inference, or simulation-based inference, for which we are going to do maybe one lecture afterwards. Okay, so this is something that we saw in the first lecture. So it's a basically summary of what a neural network does. And essentially, there are several elements, but what we have, a neural network is essentially a universal approximator that you saw with Carlos in the first lecture. And essentially, what you do is try to parameterize with some free weights, free parameters, W, a mapping between some input space, which can be whatever dimension, and a target space, which is theta. And you try to find, or with a minimization problem that you minimize through gradient descent, including a loss function, you try to find the optimal weights that actually minimize your error or your loss function, right? And because you do this with backpropagation and gradient descent, you are able to do this very efficiently. And essentially, you can have a very general functional form that can be of very high dimensions, in which your weights can be very high dimension, with, of course, no physical meaning, but you're able to essentially map quite with a small enough error any two quantities overall, right? And so there's a linear component and there's a nonlinear component, which we call the activation functions. And so it's a very flexible fitting machine, essentially. So you can fit any two quantities with an arbitrary small error, right? And so then, depending on what type of data you have and the structure of the data you have, you might use a slightly different flavor of your neural network, but the overall idea is the same. And so this is something that has been happening over the past years as well. So we've seen that when you deal with images, essentially, so things in a grid, you can use CNNs. We saw that last lecture. We'll see also, if we have some time, when you're dealing with sequences or time series, like text, you'll use transformers. This is GPT, general pre-trained transformer. And when you are some kind of non or very arbitrary data structure, you can use graph neural networks. But essentially, it's the same thing, right? You're trying to map something into another. And the only thing that you're going to change when you change the structure, it's the meaning of these weights is a bit different. Meaning that, in a CNN, for example, we saw these weights represent filters, but the structure is the same. The way you minimize it is the same, right? In a transformer, these weights will mean attention mechanism, or which words are more important for your prediction. But the way, it's just the meaning you give to these weights, but the way you minimize it, it's exactly the same, right? So this is something for now, you've only seen CNNs. We're going to attach these other things in the future. But today I want to, so essentially, today I want to talk about inference in general. So independently of the type of neural network you use, how you can estimate uncertainty, right? So we have this universal approximator. This is basically what we saw with in the first lecture. And essentially, if you have, it's just, as I said, a fitting machine. So if you have some clouds of points, you can have a universal approximator that will estimate with as small error as you want your data point. So you can have something that passes through your clouds, and if you add more and more free parameters, at some point you can even have something that passes through all the points. So it's a very flexible machine. Then the usefulness, it's depending on what you want to do. Now, the starting point of this lecture is that that's interesting, that's nice. You can approximate any distribution. However, for science, it's relatively useful, right? Because if we don't have any uncertainty here, it doesn't tell us much, right? For example, in that particular fit on the left, you see that there's very little scatter in the center around 0, so the prediction is very safe. But when you go to the limits of your X range, you see there's a scatter increase in your Y direction. And this is not at all captured by your neural network. Your network just gives you an average approximate. So if then you try to predict a point around 0, it will tell you this with the same confidence what's the value of Y. And this is not what your data is showing you, right? And so this for science is important. You can have more dramatic cases like this one, in which you have a bimodal distribution. If you fit this with a standard neural network, it will give you the mean of the distribution, as we will see later, which is completely nonsense. Okay. So what we want to do today is essentially move away for science, and we argue that for science this is what we need to do, and now it's very easy to do, but you need to move away from this deterministic mapping that a neural network is, and look at neural networks as statistical models. It means that what neural networks are doing is not a deterministic mapping between one input and one output, but they are doing is a probabilistic mapping, in which what you are parameterizing is the probability distribution or the posterior distribution of your target space theta given your input space x, right? And this, you parameterize this with your weights w. Instead of parameterizing a function, what you're doing is parameterizing a probability distribution. And now the point is how you do that. So this is where I'm going to switch a little bit to Bayesian inference, okay? And so how you typically estimate posterior distributions. So, and this is independent of machine learning. We'll make the link afterwards. So machine learning, as I said, the goal here is to try to set up a neural network that estimates a posterior distribution, which then accounts for the uncertainties in your data. So when you do standard Bayesian inference that many of you probably have done if you're dealing with data, what you're trying to do is estimate, you have some data, X, you have some model parameters, target space, theta, and then what you're trying, so normally what you try to do is the goal of your inference is to estimate, given my data space, what is the probability that my model, my parameter space, describes this data. And this is the posterior distribution. And normally it's easier to access the likelihood distribution that gives you, given my model, what my data should look like, okay? With some prior knowledge of what the parameter space is in your data, right? In your model space. And so when you do Bayesian inference, then what you're trying to do is trying to estimate this posterior distribution. So this is essentially a sampling problem. And when you don't know it, so typically what you need to do this, you get the posterior. Again, posterior only tells you what is the model parameters given my data, right? And so what you need to do when you do posterior estimation, because of the Bayes theorem, you need access to the likelihood. And the likelihood only, it's a probability distribution, again, that tells you, given my model parameters, what my data looks like, right? And that's typically something that when you don't know, the typical assumptions we do in Bayesian inference is assume that this likelihood distribution is just a Gaussian, right? So we don't know the shape of the likelihood, but we're going to assume when you are in large numbers, or you will assume that this is a likelihood distribution. It's a Gaussian distribution, sorry. And if it's a Gaussian distribution, this means that very easily you can write the likelihood, okay? Because you can analytically write the likelihood. This is what we do typically when we do inference, which looks something like that, okay? You have your model or your target space, you have your data, you have some covariance matrix depending on the dimension, but essentially this gives you the log of the likelihood. And once you assume that this is a Gaussian distribution, it's a strong assumption, then what you need to do only, because you have this distribution there, the only thing that you need to do is you're going to sample this probability distribution. So essentially you are going to take you try different values of your theta space. You want to find this posterior. So what you're going to do is you're going to try your theta space with some model parameters depending on your prior. You're going to compute for each point in the theta space, because your data is fixed. Theta is what's changing. You don't know what theta is. You're going to try what is the different model parameters. You compute the likelihood. And for this, every point in the data space, theta can be a very high dimension. You multiply by the prior, which is fixed, can be flat, and then you get a sample of the posterior, right? And so you repeat this many times, and you get samples of your posterior distribution. You don't get the full analytic form of the posterior distribution. You get samples, okay? By assuming that you can compute the likelihood, okay? That's standard Bayesian inference. And the way you do this sampling, you can do brute force and completely uniformly sampling the data space, but this is not very efficient. So people have come up with algorithms of doing that. And you probably know MCMC or Hamiltonian Monte Carlo, or these kind of algorithms. What they do is essentially they are going to try the parameter space. They are computing the likelihood. So they compute the likelihood, then they estimate the posterior, and so on and so forth. So they sample in a smarter way the parameter space, because the parameter space might be large, okay? But so this has some issues somehow, in the sense that you are making a strong assumption. You're making an assumption that the likelihood is Gaussian, which can be okay in many cases if you have large numbers. But if you don't have enough data, it's not a good approximation. You might be in a situation that you cannot write the likelihood. So simply assuming that it's a Gaussian is wrong. So if you don't have an analytic expression for your likelihood, you cannot do MCMC, you cannot do Bayesian inference, right? And on top of this, if you guys have done any Bayesian inference in the past, you know that its MCMC is low, in the sense that you need to, if theta space increases with dimension, you need to sample. You have lots of dimensions, and data space is all high dimensionality, which typically happens in astronomy. This takes a lot of time and sometimes impractical. So doing inference in spaces of billions of parameters of observations, it's complicated, right? So because just remind you that for every time you change x, the value of px theta will change, because this comes here. So if you have a new observation and you want to check and you want to get the posterior distribution for this new observation, you need to start again from scratch the sampling of all your data space. This is what we call non-amortized, right? Because for every new observation, you need to resample everything. And this takes a lot of time. Okay. So how can we accelerate this? And this is something, again, it doesn't have to do anything with machine learning, but machine learning has jumped in and helped doing this inference. But what's the alternative if you don't want to redo this sampling again, or it's too expensive? So the alternative is assume that in some cases you cannot write the likelihood analytically, for example, or it's not a Gaussian. I don't want to make this assumption, but I have a good forward model. What do I call a forward model? Is I have if I give you some parameters of my theta, my model, I can produce some mock observations. This is typically happens. We know how to do it in astronomy. Going the opposite way, the reverse problem is complicated, but having some model parameters and predicting what the observations will be. For example, on stellar populations in galaxies, you can have some star formation history, some model parameters, and then you can produce some mock colors, for example. And you can do this in many other fields, right? So you have some model parameters and you can produce some mock observations. And on top of this, you can add observational systematics like noise modeling and blah, blah. If you know how to do that, you can create easily, this is a toy example in 2 dimensions, you can create pairs of model observations, right? So I can take one model parameter and I will mimic what X would look like, okay? And I can repeat this many times. So for the same model parameter, there will be some scatter, of course. And you can, for other model parameters in this plane, of course, this is in 1 dimension. Theta is only 1 dimension. You can imagine this in high dimension. But essentially, if you have this forward model, you can sample and produce many mock observations, right, of your space. And essentially, what you're going to do, if you repeat this many times, you're going to have some covering of this plane. This is a plane, but you can imagine a volume in high dimensions of this theta space and so model space and observational space with this forward model that, as I said, should contain also observational systematics and all the systematics we know. So this, what I call forward model also contains a noise model, right? So what happens when you have that? Well, you make the assumption, which is true actually, that you are producing samples of this joint distribution, the joint distribution of theta and X, right? What your forward model is doing, it's sampling an unknown probability distribution that's the joint between your model and X. So you don't know what the shape of P is. I cannot write it analytically, but I can sample it. I can create some samples using my forward model, right? And that's something that, so assume again that these samples come from an unknown probability distribution and is the joint distribution between theta and X. So what can I do with that now? So for example, now what you can say is, okay, now how do I do inference with that? Now I have this sampling, okay, can be sparse or not, depending on how expensive my forward model is. But then I can say, okay, now I have an observation. Okay, these are just mocks. Okay, but now I have an observed X in the Y-axis. Okay, so how do I compute the posterior distribution of my theta space? So the easiest way to do it is what we call ABC, or approximate Bayesian computation. And essentially, I'm going to say, okay, my observation lies there. So I'm going to throw away all the mock points that are not compatible with my observation. And I'm just going to keep a thin delta X region that contains around my observation. And then I just plot the histogram on the X-axis of possible theta values that are compatible with my X according to my simulation. So what are all the possible model parameters that could have produced this observation? Okay, and I just plot the histogram. And that's my posterior distribution. Okay, so I've done just Bayesian inference without any MCMC and without any assumption on the analytic form of the likelihood. Okay. And this is what we call implicit simulation-based inference, because it's based on forward modeling, or likelihood-free inference, because I'm not assuming any functional form of the likelihood, or implicit inference, right? And so, again, there's no machine learning involved here. This is very old. This is from the 80s. And so it translates quite nicely what just a posterior distribution is, right? So what I'm just with my forward model, I'm able to sample the joint distribution. And by just getting slices through this joint distribution, I can estimate a posterior distribution. And this is also nice because it's amortized as opposed to the MCMC. What does that mean? So I run my simulation, my forward model once, many times. But now if I have another observation, I don't need to rerun anything again. I just move my slice over here, and I get another posterior distribution out of the box, right? There's no resampling, so it's much faster, okay? Good. So what's the problem here? Of course, this looks straightforward, but this is a toy model in 1 dimension. Now, when we do inference, in general, in real terms, theta will be high dimension, X especially will be very high dimension. So if you want to populate this space, n-dimensional space, with lots of forward models to have enough data points when you do this when you do this cut in the X space at very high dimension, you need lots of simulations, right? And this very quickly, this ABC computing, when you apply it to real science cases, it's not very practical, okay? Because I end up in the same situation. I spend lots of time running my models. But this is where machine learning comes in and goes back to what I was saying about using machine learning to do probability estimation. In fact, this is in the machine learning problem. What I'm facing here is what I call density estimation problem. What does that mean in machine learning? Is exactly when I have points that I know, samples that I know come from a probability distribution, but I don't know this probability distribution. I want to approximate the probability distribution based on samples, okay? This is density estimation. It's a very well-known problem in machine learning, okay? So we can use machine learning not to try to get an estimate of the probability distribution based on the samples, okay? So we are going back to what I said at the beginning, trying to use neural network to approximate probability distributions. And we're going to use it by sampling. So if we have a forward model, and I can use machine learning to sample or to estimate P based on the samples of the forward modeling, I can do Bayesian inference very efficiently, okay? Good. So this is where machine learning comes in, and essentially tells you that, so this is density estimation, which I just summarizes what I just said. If you have a data set, the goal of density estimation is to fit a model to this data, to the data so that we can generate new data points by sampling from the distribution, right? So essentially what you want to do is have an approximate something based on samples, try to get an approximation of the joint distribution that you can just call the neural network, and it will produce new samples of this data space. And you can also probe the neural network, and it will give you some probability value of a given point, which is exactly what you want. Right. And so, as I said, and so what we call simulation-based inference, or what I just described, is then a density estimation problem. And if you get access to the full distribution based on the data points, you can simply, once you have an approximation of this joint distribution, you can very quickly, in an amortized way, sample from the posterior distribution, or you can also evaluate the likelihood if you do cuts in the other way, okay? So the joint distribution contains both. On the y, if I cut in the y-axis, I get the probability, the posterior distribution. If I cut on the x-axis for a given theta, what are the values possible of x? This gives you access to the likelihood, okay? But if you have a neural network that can approximate the joint distribution, you can access both, right? Good. And so then then how do we use this to do inference? And we'll go back to that. But essentially, you can use a neural network to approximate either the likelihood or the posterior, okay? So you can use a neural network to approximate on the y-axis or on the x-axis. And then you can just do, if you do, for example, the likelihood estimation with a neural network, then you will still need to do the sampling, okay? But instead of assuming that the likelihood is Gaussian, you are going to call your neural network that will give you a value of the likelihood. So you're not assuming a parametric form of your likelihood, you're calling the neural network. The neural network for every point in the data space will give you this is the likelihood, and you do MCMC normally instead of assuming the Gaussian distribution, okay? But you can say I want to do amortize just as ABC, and I don't want to do the resampling and the MCMC every time. I just want to get the posterior distribution for every, so my neural network will directly go to the posterior without any sampling, okay? This is what we call NLE, neural likelihood estimation, or NPE, neural posterior estimation, right? So the point is, how do I do this with a neural network? And lots of things have happened in machine learning over the past years that have made, so there's been lots of works in architectures and ways of making this estimation of density, density estimation very efficient, okay? So again, the implicit likelihood, the simulation-based inference is a very old problem. We didn't have good ways of doing it. And with the deep learning revolution, we have found, or there's been developments of very efficient neural networks architectures that are able to very efficiently estimate densities with a cloud of points. Okay, so again, the problem is easy. I have a cloud of points here that can be multimodal, complex, and I want to build a machinery that is able to estimate the probability of every point. Right? So that I can call it either as a likelihood sampler or as a posterior estimation. And deep learning, what has allowed over the past years is to do this at very high dimension and very efficiently, so that it opens the door to very fast inference. Right? So, I'm going backwards. So, over the past, the next couple of lectures, so I'm gonna give you an example now how to do it. But the idea we had is to show you some examples of more concrete examples of how you do this with neural networks and the different architectures and approaches you can use. And there's several people in our group working on doing inference in astrophysics with different approaches. But essentially, the main message here is that you're going to use your neural network to estimate the posterior distributions. Now, in order to show you, I'm going to show you now the easiest way of doing it, which is just a straight and just an example of how to code it, which is the most basic way of doing this density estimation with neural networks. And actually, I would argue that at least any paper or any scientific analysis that uses neural networks in the work should at least incorporate this basic uncertainty estimation. Nowadays, I think it doesn't make any sense, and we still see papers like that just throw a neural network into scientific data without any uncertainty quantification. This shouldn't be the case, and it's extremely straightforward to do it, right? So just to understand how to do it, so again, just if you have questions, let me know. So I want you to understand what's the basic problem we are facing. Essentially, it's just a sample of points, and we want to estimate the underlying probability distribution that has created these points. And then you can put this in any loop, okay? But that's the basic, yeah. Well, when you put it that way, yeah. Well, but you can do density estimator without neural networks. That's what I'm going to say. So this is, again, you can do kernel density estimation, for example, or fit a bunch of Gaussians to that. But this doesn't scale very well at very high dimensions. Okay. So you have ABC, like it's the simplest way, but you can also indeed do KDE, kernel density estimator. Maybe you know, there's no machine learning involved. You just fit some Gaussians to that. But when it's very high dimension, it doesn't work. And in practice, so essentially the only thing that machine learning has brought into the table here is efficient ways of doing it that scale very well at high dimensions. That scale, so for example, I'm talking about, so this is a toy example, but at high dimensions, I'm talking the space of images. So when you have these neural network models that generate fake images and fake videos, what they are doing is learning the probability distribution space of images and then sampling this probability distribution, right? So you are the probability distribution space of images of n pixel by n pixels is huge, right? Imagine learning this probability distribution with KDEs. You can't. It's not a bunch of Gaussians. It's a very complex, very high dimensional probability distribution. Now you throw to them diffusion models, for example, which is a kind of density estimator with neural networks, and you can generate extremely realistic movies and extremely realistic images, right? So that's the space we're dealing with, okay? Now in Astro, it's probably not that high, But essentially, that's the regime we're talking about. But it's only a way of doing this efficiently. And we didn't know how to do that. And yeah, so now we can even learn the space of videos, for example, right? So, but go back to a toy example and how you do this in the not. So we're going to talk later if we have time about diffusion models and so on. Now we're going to keep it simple for that particular case. So let's go back to what a neural network does. It's now not probabilistic, the simplest one. And so essentially, assume we have this cloud of points that I showed you earlier, and we want to fit these points with a neural network, okay? So what the neural network is going to do, essentially when you do just a simple neural network with a mean square error loss that we've seen in the first lecture, the only thing that we do is we make the strong assumption that the posterior distribution of, in that particular case, y given x, sorry, I changed the letters, but if I take a cut in x here, and I want to have the posterior distribution of y given x. So what's the possible values of y given my x? This is what I want to estimate when I feed this data. And then for different x, what are the possible values of y? What I'm going to do is, if I take a simple neural network, I'm going to assume that at every x, my y is described by a Gaussian distribution. The distribution of, so I take the green band there, and I plot the histogram of the points within these green bands, and I'm going to assume that this is a Gaussian of unit 1, so sigma 1, okay? So it's a strong assumption. So when you throw a neural network to that, what you're assuming is that in bins of x, you can describe all the data points at a given infinitely thin delta x, you can describe this as a Gaussian of sigma 1. Okay, which clearly it's not the case because the scatter might change, right? But that's the strong assumption you are making if you don't do anything to a neural network. Okay, just a little bit of math so you see it, but it's very easy. So why is that? Because when you train a neural network, what you're going to assume is that every pair of points xy, which is your training set, it's an independent realization of some samples, and you're going to say, I want to find the underlying probability distribution of y given x. So precisely if I give x, what's the underlying probability distribution? And I have a samples of points. So what I'm going to do is essentially maximum likelihood estimation very easily. And what I said, I'm going to assume that the distribution at a given x is a Gaussian. Okay, and that gives me, so I skip the details, but that gives me what's the likelihood of a given observation. And I'm going to parameterize my neural network, the mean of this Gaussian. Okay, so graphically, what does that mean? That I'm fixing sigma to 1 for a given x, and I'm trying to find the mean of the Gaussian distribution in every delta x. I fix sigma to 1, and I'm going to find the best mean of the Gaussian distribution that explains my blue points. Okay, so essentially I'm fitting means of little Gaussians of sigma 1 in delta x, right? And mathematically this is translated because I'm assuming it's independent points by multiplying the likelihoods of every data point, assuming that what I'm learning is the mean of the Gaussian, which is there. So my neural network is learning the mean of the Gaussian, essentially, okay? So because it's independent, I'm multiplying likelihoods, and this becomes my loss function. This is what I want to find, okay? I want to find W so that this likelihood is maximized, which means finding the mean, maximizing the mean of this little Gaussian. Now, if you look at this expression, everything is constant here, except my mean, which is I'm trying to fit, that depends on my input, my Y, that's my training set, my output, and then these are all normalization. Because I'm assuming sigma equals 1, it goes away, and I get this thing, right? Okay. Now, typically when I do inference or minimization, I'm going to take the likelihood to transfer the log to transform the multiplication into a sum, which is always easier. And if I assume sigma equals 1, I go back to this mean square error. Okay. So, and when I do mean square error loss in a neural network, the only thing I'm assuming is that it's a Gaussian likelihood, and that I'm fitting means of Gaussians at every delta x, essentially. Okay, but I'm making a strong assumption here, which is that sigma equals 1. Okay, and goes back to my point at the beginning that when I look at this data, clearly there's some regions there where the scatter is much larger in my data space, and regions where my scatter is very small. Because I'm fitting only the mean, the neural network doesn't know anything about that. It's just capturing the mean of the distribution. And this is when you end up with a line that goes over all the points, but it's the mean of the distribution. So if you go back to this here, sorry, I don't know. This red curve here, which is fitted by a mean square error loss, is just the mean of a given delta x is giving you the mean of the distribution. That's the only thing it's doing. Okay? And the more flexibility you have, the more finer your mean will be. But it's just the mean of the distribution in a given delta x, assuming a sigma 1. Okay? So it's a very basic density estimator with a Gaussian with one parameter. Now, what's the easiest way to make this a bit better? Well, question is one parameter enough to describe this distribution? Well, we clearly see that it's not here in that particular toy example, because again, in the red line, you have a very small scatter for a given x. In the blue stripe, you have a wider scatter. And how do you capture that? So how do you improve your density estimation so that your neural network captures that? Well, it's very easy because neural networks are extremely flexible. So the easiest answer and the easiest way of doing density estimation with neural networks is what we call MDNs, or mixed density networks. And this is what I say that it's very easy to incorporate into your scientific workflow. It doesn't require any specific knowledge of machine learning. It just adds some extra layer and gives you at least some inference and some uncertainty quantification. So for now, I'm saying if you do a standard neural network, you're assuming that your posterior distribution is just a Gaussian and you're fitting the mean. So what you're going to do is, instead of assuming that at a given x we can describe, you can just fit the mean, we are going to fit as well for the scatter. That's very easy, okay? Which means that instead of having one unique parameter at every delta x, we're going to have two. One that tells me what's the mean, and another what tells me what's the scatter, right? And we're going to learn both of them with a neural network. For now, we know how to learn the mean. We are using mean square error loss, and we know we are learning the mean. We can change a little bit the loss function to learn also the scatter. And this is what a mixed density network does, okay? So how do you do that? Well, it's very easy. So you're going to take your neural network, and now your neural network, instead of outputting one value, like the y, it will output two values, okay? Which don't have any meaning. Just the neural network is very flexible. You just tell the network now output two values. I don't want one, I want two values. We call them mu and sigma, but they don't have any meaning until I put them in a loss function. And so then I take these two values and I write again the loss function, assuming again a Gaussian likelihood. But then my loss function is going to have the first parameter, the first output from a neural network will go into the mean. That one is going to learn the mean. But I have the second parameter is going to be learning the sigma. I'm going to characterize the sigma by the weights of the neural network. So the weights of my neural network will learn both the mu and the mean and the sigma of the distribution. And you see, it's nothing changes here. It's just that now the neural network enters there in the likelihood function. So I cannot just simplify and remove the sigma equal 1. My loss function is a bit more complicated, but nothing very tricky. It's just that I'm adding an extra term, okay? My neural network is now outputting two parameters, and I'm taking these two parameters and plugging them into the loss function, okay? My neural network doesn't know anything about mu and sigma. It doesn't know this first parameter is mu and the second parameter is sigma. It just learns it through the loss function because it wants to optimize this likelihood, maximize this likelihood. So it will learn to encode the sigma and the mu into the values as it learns, okay? So let me show an example of how to do that in a notebook. Hopefully I have something here. Okay. So this is another toy data. I will share the notebook with you. Again, I created some artificial data set, exaggerating the difference in sigmas, right? And I want to fit this with a neural network. So you can do this with a first deterministic mean square error loss, okay? And again, this is PyTorch, but it's very easy. Where's the loss function? Somewhere here. Well, it's a MSC. I don't know where I put it, but there should be somewhere where I define the MSC. Anyway, this is just fitting the model. And if you do this model fit, this is exactly what you get, right? Mean square error loss, assuming sigma equal 1. So the model is going to work very well where there's no scatter. And when there's scatter, it just tells you the mean of the distribution, right? So now you use this neural network to estimate the value of a given data point. If you are in this regime there, it would be very uncertain, but you don't know. Of course, here you can visualize it. You are in 1D. Imagine you are in n dimensions. You have fitted lots of data points, and now you use your neural network to predict stuff, to predict redshifts, or to predict whatever. You might be in a region that you are here, and your model is, your neural network is just throwing a value, or you went and telling you it's the same relevance when it's really not, because your data it's not the same. So here you can visualize it, but this is what the deterministic, and it does exactly what it needs to do. It goes to the mean. It cannot do anything else, right? Now let's gonna assume that we are adding two terms. So now we are fitting mu and sigma. And again, it's very easy because with PyTorch it's very easy, but essentially now my neural network outputs, so it gets H, which is the output of the neural network, and then I'm going to transform these into 2 points, mu and sigma, right? And then my loss function is the Gaussian likelihood, which is essentially, it's using a normal distribution, and I'm taking the mu, the output of the neural network as the mean, the other output of the neural network as the standard deviation, and then computing the log probability or the log likelihood. Because I'm using a pre-built function from PyTorch, but essentially I define this as a normal distribution. So I just call this object here and compute the log prob, which is the only thing that it's doing, it's computing this thing. Okay? So I'm plugging in the output of the neural network there, plugging in the neural network output there, and then computing this. This is what this loss function does. So I've it's extremely simple in terms of implementation. I haven't done anything. It's just defining my loss function. Instead of writing MSE, I'm gonna write a likelihood function. Okay. So I train these, and now I can plot my neural network outputs 2 points, the mu and the sigma. And so now, depending on the X space, I can plot what is the prediction, the mean value, and the uncertainty that the neural network has predicted on that data point. And you can see that the neural network learns very efficiently that the sigma is very small where there's no scatter. And as soon as you have scatter, the sigma increases. The neural network has learned that. Okay. So now when you ask the neural network what's the output for that particular space, it will tell you, okay, the mean is this, but be careful. You know, the error bar is huge. Okay. So very easy, you have incorporated some error bars. And because I'm assuming that this is a very simple Gaussian distribution, I can now also call the neural network and compute what's the likelihood, the value, because it's just the value of a Gaussian function. For every point in this XY space, I have a value of the likelihood, which is just calling the likelihood function. So I can compute what's the value, the probability of every point in that space. Okay? I'm doing density estimation. So I'm transform these data points into a series of probabilistic values. And now give me a point in every, whatever point in the space, I can give you what's the likelihood of this point. And you see that this is what I'm plotting here. I'm plotting directly the likelihood of the Gaussian distribution with the arbitrary value. But you can see here that it's very high there. Why? Because the distribution is super peaked, right? Because when I'm here, the values that I can get are very, very constrained. So the distribution is extremely peaked, so it gets very high values. While when I'm here, it's a very flat distribution. Sigma is very large, so I get very low likelihood values for that particular point, right? So we are transformed. We are just transformed these points into a density with a very, very simple prescription, okay? Again, this is a toy model example. When you go to image space, you cannot just do this mixed density network. You need to do things more complex, but again, it's the same idea. You are basically trying to find the architecture to estimate density from a series of points. Questions? Good. Now, what happens if I have this distribution now? Imagine you have this distribution over here, and I try now to play the same game. I'm going to take my neural network. Now I'm happy because I know how to estimate uncertainties. I'm going to give mu sigma and trying to fit this. What would I get? What would be the prediction of my neural network when I fit this distribution? You're going to take the mean of the distribution and the sigma, right? So the best thing it can do is this, right? Because I just gave the neural network 2-parameter freedom. And so why it doesn't go exactly through the center? Because when I generated this data, I gave higher probability to be in the lower branch than in the higher branch. So it learns that the mean is a bit lower, but it tries to fit the mean of the distribution, and since it's a bimodal distribution, it just fails. So again, if you don't know how your data is and take brute force neural network, it's not a magic box. It's doing these things, right? Now you can imagine this in high dimensional space. You have multimodal distributions. You run your neural network and you think, oh, it's working fine, or it's not. But actually what it's doing, it's just thing, it's not magic, okay? And so here it clearly says that, well, it's uncertain, but the value it gives me as a most likely, or the mean, is completely wrong. It's actually where it shouldn't be. Okay. So how do I improve that? Well, I can play the same game and complexify the mixed density network. That's why I call it mixed density. That's the easiest way to do it. And the one I'm going to do is, instead of having 2 parameters that output the neural network, I can say, no, I'm going to have 4. Okay, or 5 in that particular case. I'm going to fit, I'm going to assume that now there are not, at every x, I'm going to assume that there are 2 Gaussians. I can fit these with 2 Gaussians, which means 2 means, 2 sigmas, plus a normalization factor so that the integral is still 1 and I have a probability distribution, okay? Because the goal is to have a probability distribution. So this doesn't change anything. It's just that my likelihood function, my loss function becomes a bit more complicated. I'm still assuming a multimodal Gaussian, so I can still write this analytically. And now I need to be careful and take the different means and put them where they should be. And giving, again, the neural network doesn't know anything about what the values are. It just learns them through the loss function. Okay, so then I plug the outputs of the neural network into the loss function, and I write this likelihood. But nothing changes. And if I do that, this is what we have here, a mixed density network. Now we have several means and scales that are not just one value. In that particular case, I created a parameter here. So I put it at 2. 2 implies that I have 2 Gaussians, so 5 parameters out of my neural network. And I can write the loss function the same way here. Okay, and you see in PyTorch is very agnostic because I just decide, I create my normal distribution, but now it learns automatically that it's a multimodal normal because my dimension of the means and scales. And to compute the log probe, I'm just calling this thing the same way. So in PyTorch is very easy. So PyTorch doesn't care. You never need to write this thing. You just tell it's a multimodal normal, just write the likelihood. And you go that way, you feed these, and this is what you get, right? These are samples from for my neural network, okay? So my neural network now has learned that the distribution is bimodal. So if I call my neural network for a given x, which are the black points, sometimes it will give me points in the upper branch, sometimes it will give me a point in the x branch. in the lower branch with a probability, which has learned from the data. Okay. And if you do the same exercise and plotting what's the PDF of my data points, you clearly see that it follows this bimodal distribution. Okay, so it has learned that the distribution is bimodal, and that you have the likelihood of the points, it's in these branches, and in between the likelihood is 0. So it doesn't output anymore any point in the empty regions, or very, very unlikely. Okay, so very simple. I can model more complex probability distribution. And then you can play the exercise. This is just moving in the X space here. Okay, doing cuts in X space and plotting what's the probability distribution that it has learned, right? And you can see here how as you go into the extremes here, it learns a bimodal distribution. Okay, when you're in the center, it has learned that it's unimodal. Okay, so the network has learned that when you're in the extreme, it becomes multimodal because you have the freedom to do that. Okay, and now when you sample this distribution, you get points where they should be. Okay, I think I'm gonna stop here. And so the message is again that it's very easy to implement uncertainties and then look at your data when you fit data with a neural network. This is density estimation, and again, MDNs work well in these toy examples. When you do a more high-dimensional inference, like images or this kind of space, you need to use other techniques, but the idea is the same. You don't do any deterministic neural network. You always do probabilistic neural networks that describe your data in a better way. Yep. Thank you. I'm happy to take questions if you want. If you are more. Or... Yep. But how does one, when you're done, this point is this bound. Right. So that's a good point. In that particular case, so what we are doing here is estimating what we call the aleatoric uncertainty. So it assumes that so the network is learning your errors, essentially, because the scatter that we see in the data points come in fact from the errors. Okay, so the network implicitly learns the errors that are in the data points. Now, if you have some specific data points, so essentially the assumption we are making here is that this scatter that comes here, it's from the errors. So the network is learning, the uncertainty it learns, it's because it's implicit to the data. Now, if you had, so there are two convolved errors here. One is that the distribution is bimodal per se, but then you have uncertainties in the observation. So we might have that if you have new observations with better signal to noise, this scatter here will decrease. And this is what the network is learning. So it's normally implicitly learned. Now, you might be in a situation in which each data point here, you know very well the error, and then you don't want to weight them in the same way, right? You can feed this to a neural network, and it should learn it. But there's no obvious way of dealing with heterogeneous error bars, let's say. So you have very complex error bars. The best way is to feed them to the neural network, and so that it takes them into account, or you weight the points based on the inverse of the error bars, for example, if you don't want these points to count as much. But what you do when you do this thing is just assuming that this scatter translates your measurement errors, essentially. Yeah. I have a solution which is not that well points. It's just, for example, the mean or something with an error bar. It's a good idea to use for the error using the loss function, a combination of the observational error and the model error. What do you call that, the model errors? So, the sigma, which the model returns of the variation. Yes, you could essentially say this will mean somehow that you think that your errors that you scatter there, it's underestimated somehow, and you think that there's an additional term of error that should be taken into account, right? This is what you're saying more or less. Of the variance of the variation of the model and the variance of the you could do that, yes, but again, it depends on the context. So I'm not sure I exactly understand what you're saying, but of course you can be creative with your loss functions, and you think that you need to capture an extra term, you can add them. Okay, if it's just a constant term that you are adding, it doesn't make much sense. But it's something that changes with X that depends on the input, then yes. Right? If you know what it actually is. Yep. Yeah, that's the limit. That's a part of the mixed density network. You don't know. So it's easy to see so the best answer is you try and you see if it doesn't improve any of your performance, let's say, which is a standard answer on machine learning. But that's also the limitation of mixed density networks, is that it's still parametric in the shape, right? You're still making some assumptions. And so this is where more modern techniques like normalizing flows that we're going to see maybe, and diffusion models, you don't have these constraints. You just let it free and you don't assume any functional form, right? But that's the limiting point in anything is, because so you don't know. Essentially, the answer is you don't know. You typically start small and then see if, by adding extra layers, you get more bimodal distribution. It means that there's some bimodality there. But yeah. Yeah. That's the trick. I mean, I think the main bottleneck of implicit likelihood inference or simulation based inference is precisely that. So what deep learning has solved over the past years is the inference. So if a few years ago, I mean, maybe 10 years ago, we didn't know how to do inference in very high dimensions. So because we were limited to MCMC, and that was the bottleneck of any inference in science, essentially. Now, I would argue that this is solved. So even if you have very high dimensional space, you know how to do the inference. But the bottleneck goes to the forward model. So if you don't have a good forward model to reproduce your observations, then all this thing is useless. Now, how useless it is and how bad is how good needs to be your forward model, because nobody has a perfect forward model, because otherwise there's no point in doing inference because you know the answer. So there's no perfect forward model. But how big or small needs to be your model misspecification. That's the key word. And that's a very hot topic in machine learning, model misspecification. So how reliable needs to be your forward model? This depends on the application. But I would argue that at least it needs to contain some observational systematics. If it's too unrealistic, you will get some answer, but it's probably biased posterior. Now, the other thing that you can do that I haven't talked about is you can also apply some what we call posterior checks afterwards. So you can check whether your posterior is well calibrated. And normally, you should be able to track down model misspecifications. But it's not trivial. So the answer is, it's ongoing research, essentially. Yeah. Okay. So thank you.